Right, today we're going to talk about some details about the electromagnetic spectrum. I've been referring to it mostly as light because that's what most people are familiar with, because that's the part that we can see. But there are a whole lot of other pieces to the electromagnetic spectrum besides just light. And so today we're going to talk about what those are and what the differences between those types of waves are. But let's start with visible light first. Visible light can be broken down into a whole lot of different colors, which if you've seen a rainbow, you've seen that happen. And the reason that it happens is because, as we've already talked about, when light waves enter different substances, their speed changes. And again, this is something that as we talk more about light when we get into chapter 22, we're going to talk a lot about refraction. But when light enters a different substance, it's going to bend. So let me explain that from this perspective here. You've probably seen on TV or maybe in person, you've seen a marching band. And so let's say that we've got a marching band and it is traveling this direction across a football field. They're performing at halftime and they're wowing the crowd and everybody's all excited. But then what happens as they go across the field, there is a mud puddle on part of the field. It's not on the whole thing, it's not all the way across, it's just on part of the field. And so what happens is that as you get here, when this part of the marching band gets into the mud puddle, it's really sticky and it's really dense and it's really thick and they're trying to keep up, but their shoes are getting stuck. And so they can't march as fast as the rest of the marching band is. And so this half of the line is marching faster and it's actually getting ahead. So you can see that it would get ahead of this part. Now, picture what would happen if instead of having a straight mud puddle, let's say that the mud puddle was more slanted across the field like this. So again, as the band goes across, this guy's going to hit it first and he's going to get slowed down. And so he's going to start to slow down and then this guy goes a little bit faster and then he hits it and then he gets slowed down. This guy keeps going and he doesn't slow down until he hits it at this point up here. These guys don't ever slow down and they're going to be all the way up here. So as you can see, what's going to happen is that the marching band suddenly is not going to be in the same type of straight line that it was when it started. It's now going to have this more of a catty corner orientation because they hit this mud puddle. The same type of thing is going to happen to a light wave when it enters a different media where it's going to travel slower. So if it enters water, if it hits glass, it's going to slow down from when it was traveling in the air and it bends, just like the marching band was no longer in the same path as it was before and it bent. So not a foolproof explanation there, but hopefully that does help you understand at least a little bit why a light wave is going to bend when it goes into a different medium. So if you've seen a rainbow before, you know that it's red, orange, yellow, green, blue, indigo, violet. I didn't have quite all those colors of markers, but I figured you could fill in the rest from your experience. I do want you to have memorized the order of those colors. And if it's not something that you've ever learned before, you can remember the order of the colors by thinking of it as a man's name, Roy G. Biv. So it's red, orange, yellow, green, blue, indigo, violet. And the reason I want you to have it memorized is this. The reason is because red light has the longest wavelength of all of the visible light. So that means that violet has the shortest wavelength. And the reason that I can remember this is because the red is on the top of the rainbow. So that means this arc is the longest. And so that helps me remember that red has the longest wavelength. Now, if you remember, wavelength and frequency, if one goes up, the other one has to go down. So if this has the longest wavelength, that means that violet light is going to have the highest frequency. And what did we learn about the frequency of light waves? Well, we know that frequency also means that the higher the frequency, the higher the energy that that light wave has. And this is going to make more sense now when we get down into the rest of the electromagnetic spectrum. Because just like there are sound waves that we cannot hear, like remember we talked about the infrasonic waves and the ultrasonic waves that we are not able to hear because their frequencies are either too low or they're too high for our ears to be able to detect. There are also frequencies of light, of electromagnetic waves that our eyes cannot detect. And the visible light is actually a very small piece of the entire electromagnetic spectrum that I have laid out here on the board. And again, this is something that you need to have memorized, but I'm going to show you how you can put this together and remember it. So visible light is going to go right smack in the middle. And here's your Roy G. Biv. And remember, R goes down here. So this is the end with the longest wavelength. On this side, next to the red, is the infrared. And infrared light, they're next to each other. So that's how you can start to remember that order. The infrared light is used a lot for heaters in restaurants. Like if you've gone into a restaurant and you see these lights that are over the French fries to keep the French fries warm, that is an infrared light. Yes, we can see some red light coming off of it, but most of what's coming off of it we cannot see. And so, again, most of it is not visible, even though we can see a little bit of the red light from this end that's coming off of that light. So infrared light is next. And then the next light after that is microwaves. Yes, the very same type of microwaves that come from your microwave oven are a part of the electromagnetic spectrum. So they are down here. And then at the very far end of the electromagnetic spectrum are radio waves. Now, radio waves are subdivided into the types of communication that we get from them. AM, FM, and TV. Radio waves are all slightly different from one another. AM waves have the longest wavelength and TV have the shortest. And so if you remember that red has the longest wavelength of everything in the visible light spectrum, as you go this direction, the wavelengths just keep getting longer and longer and longer the further this direction I go. So this end of the electromagnetic spectrum has the longest wavelength of all of them. So this end these are not dangerous waves because they don't have a whole lot of energy. We get hit by radio waves all the time. You go outside and there's a radio broadcast and TV broadcasts going on all the time. You never notice getting hit by a radio wave. We're not worried about standing too close to the microwave. People used to be worried about it before they understood it well. But we don't worry about standing too close to the microwave and getting exposed to microwaves because they don't pack enough energy to be dangerous to us. So these are the longest wavelengths on this end, and they have the least amount of energy. Now let's look at the opposite end of the spectrum. We said here that the violet visible light, when we talked about it up here, we said violet in the visible light spectrum has the highest frequency and the highest energy. So when you think about ultraviolet light, ultraviolet is going to be right next to the violet. So here's violet, here's ultraviolet. Ultra is just beyond violet. And so that is going to come next. Once we get down on this end of things, these waves have enough energy to kill living tissue. And so medical facilities will use ultraviolet light to sterilize instruments, to kill the bacteria on instruments so that they can use them doing medical procedures and they don't worry about risking infection. So ultraviolet, X-rays have an even shorter wavelength than ultraviolet light does. X-rays, you probably are aware that if you have too many X-rays, they can start to damage your body. So doctors will often try to keep the number of X-rays they ask for at a minimum. That is also why when you go to have an X-ray done, the X-ray technician will position you in front of the X-ray machine, and then she will often go stand behind some sort of it's often a lead barrier, so that those X-rays can't get to her. It doesn't do her any good to be exposed to the X-rays, and that long-term exposure could be damaging to her health. So the technicians always shield themselves from the X-rays because the continual exposure to them would not be safe. In small numbers, X-rays are very beneficial in diagnosis, and so that's why we can do small numbers of them as long as we don't just overdo it and get tons and tons of X-rays all the time. Gamma rays are produced by radiation, and they're produced by nuclear reactions. And again, we'll talk more about gamma rays when we get into our section on nuclear chemistry, much more towards the end of the school year. But these gamma rays are going to have the very shortest wavelength, because the longest wavelength's on this end. So these have the shortest wavelength, but that also means that these have the very highest frequency. And so that also means that they're going to have the highest level of energy. So what you can think about is that the waves down here have a long wavelength. If they're on this side, they don't cause any kind of damage to humans. These may look more dangerous because it's red. You don't think about microwaves, although they can cook your food. And so as you go this direction with things, longer wavelengths, less and less energy. Again, you get hit by radio waves all the time. You don't think anything about it. But on this end, these types of things are the things that we try to avoid and stay away with, although we do utilize these to our benefit in different types of technology. So ultraviolet X-rays are more dangerous. Gamma rays are even more dangerous just because of the amount of energy that they will give off. So that is an overview of the electromagnetic spectrum. And hopefully that makes a little bit more sense, gives some perspective to it as you look at the diagram in the book and compare those as well.